In this video, I'm going to do a quick EMC EMI review of an open source industrial printed circuit board. First, I will take you through a hands-on look at the board and show you how I spot the potential EMI issues right there on the PCB. Then we'll jump into a layout simulation using the electromagnetic and signal integrity software Simber, so we can double check those first impressions and make sure this board is ready for EMC testing. The design you're about to see comes from Gabriele Marocco, a great engineer, member of the EMI Control Academy, of course, and someone who also shares a lot of knowledge on his YouTube channel. If you're new here, my name is Dario Fresu. I'm a fourth generation electrical specialist and I'm the CEO and principal EMI engineer at fresuelectronics.com, where we help engineers in small and large companies master EMI control and electromagnetic compatibility in their design. Let's take a look at this board. So first impression, design looks pretty clean. I like the way this is designed. I see maybe in here already between the 86 signals, this one, they are running parallel. So I think that we can improve a little bit the spacing in here. We move this trace a little bit more here and also this one here, just to avoid some crosstalk, because it's easy for the signals to couple to these traces when they run parallel like this. Now this is the breadboard point. I think this is where we do the testings. This one here should be with the LEDs. So the LEDs are SMD mount. Then we have in here the main processor. Let's see, this is the ESP32S3, okay? And then in here, I suppose is the isolated part of the board. Then in here, what we have, some communications. So one of the things that we need to take care of, you see, when we don't place the name of the nets in the schematics, then we have this problem in here that we don't know really what kind of net is this one. So what is in this net? And it becomes a little bit difficult because the PCB layout tool assigns the nets automatically. So it gives just random names. So it's important that when we design the schematic, we try to assign to each net the specific name that we want. For instance, we take this net in here and we provide a net name like we did in here. So in here you see there is the SEK. Okay, so let's take a look at the bottom layer just to have a quick understanding, and then we jump into analyzing the layer stack. So even here, a little bit of spacing. For instance, we can separate this one a little bit on the side. This is also a communication net, so we have to be careful that we don't want to couple any of the signals into a GPIO, for instance, because we never know what this GPIO is going to trigger. So maybe we have a reset line that is triggering some other boards or even internal resets. So we want to be careful how we design these nets. We want to be meticulous about how we design the layout. What I like already is that we have some GND VS placed all over the board. As you can see, this will become important because what it does is when we connect the layers together, this is stitching the planes together, especially if we have a Stackup where layer 2 and layer 1 are both the ground plane, so the return and reference plane for the signals. I would expect in a board like this. So pretty clean. I would improve a little bit with the spacing between the nets and use more the space of the board. So this one here, perhaps I will enlarge it a little bit more so that I can have more space between the nets, because you can have also some coupling between the power nets and the other signal nets, which can induce some noise into the signal lines or vice versa. So the GPIOs, maybe they have some fast rise time signals, and then they can induce some noise into the power lines. So we want to avoid this type of mistakes right from the get-go. Okay, now let's analyze the Stackup in here. So we see that we have 4 layers. We can see it in here, but also we can check it in here where we have the physical Stackup of the board. So here it tells us we are using this Stackup where we have signals. Otherwise you will have, for example, you can choose power plane and then assign the net from this Stackup manager, so the board setup manager. Okay, let's see the physical Stackup. So we have some copper, then pre-peg, then the copper, then we have the core in the middle, and you see the separation here is the same for the core and also the pre-preg. So 0.023 millimeters, then we have 0.035 millimeters for the outer layers, but also for the inner layers. Okay, so just a quick look in here if we have some more details, some constraints here of the board. I just wanted to see how he selected the boards in here, net classes. So he divided the 50 ohm antennas, the power lines, USB, and then the default. Okay, so let's see more in detail in here. First layer layer is the signal layer. So here we have main signal layers, and then we have also on the bottom layer, we have more signal traces. So what's important in here? So if I have a signal layer on the top, the second layer is automatically the ground plane. So the return and reference plane. So we avoid calling it ground plane because a ground plane can be a little bit misleading, because ground plane is to refer to chassis, to refer to earth ground, to refer to digital ground, to refer to anything nowadays. So we want to be specific. The second layer in here should be the return and reference plane. And what does it mean, return and reference plane? Because it has to provide the return path for the current and for the signal currents when the signal is propagating. So the signal, when it propagates on the top, is at the same time also propagating in the return and reference plane. In here, we want to minimize the current loop. And so when the signal propagates, the signal current propagates on the top, but also on the bottom at the same time. The main point is that we want to have adjacent to the signal layer the return and reference plane here. And so the second layer is exactly what we expect. So a full plane, there are no cuts in here, there are no splits, there are no segmentation of this board, because we want each signal when it's propagating has underneath the return and reference plane. So we said return, but also reference. Reference because we want to provide the reference potential when the signal is propagating. We have to forget this, that the electrons propagate from the top, then reaches the load in here, it comes to this point, and it continues on the bottom, and then it reaches the load. Let's see where this one leads. In here. This is not how the signal propagates. So it does not propagate in here through the signal trace, then reaches this point and come back. But this is instantaneous. So the signal propagates at the speed of light in the dielectric. At the same time that is propagating on the signal trace, is also propagating on the return and reference plane. So we have to think in terms of fields. So the fields are propagating in the dielectric in between the signal traces, but also is layering here. So they are just in between. So is not propagating on the top and then goes on the other layer, but is propagating in the space in between these two layers. This is super important because this means that we have to channel the signal all the way through this path in here. So the signal is channeled between the red trace, but also in between this green plane in here. We want to be careful about that. The signal is propagating between these two layers, not first on one and then later on the other one. So when we're channeling the signal, maybe we can take a look also at the 3D point of view, because I want to show you the signal propagates between these layers. So in between these two layers in here. So the signal propagates between these two layers, not on the top in here and then continues on the bottom. Now, what else we need to take a look in here? If the stackup is not correct, then EMI and EMC, so that the EMC test, will be a problem later on, because the signal will not be channeled in here and then they will spread out of the board. So they will radiate out of the board, especially when we have the cables connected to this. So these will act like the antennas for this board, because in this board we provide the energy from the power supply, but then these IC in here will convert the energy into signal. So it will be also modifying this energy and will be transforming it into fast switching energy points. And this means that we will create some harmonics in this process. So these harmonics is what contain the energy at different frequencies. And this is why we need to be careful, because different frequencies will interact with the geometries of the boards differently. So maybe some traces in here will act as antennas for certain harmonics and will not act as antenna for other harmonics, but this is exactly the point. So we will have different frequencies in here with different levels of energy, and we want to be careful not to create antenna-like structures in here that can promote the radiation outside of the board. So we want to contain the signals and channel them so that we can redirect them where they need to go. So the stackup follows certain rules. So if we have a signal layers, the adjacent signal layer has to be a return reference plane so that we can channel the signals in between these two layers. So the layers always go in pairs. So if we're talking about RF, this is a little bit different and depends on the type of application that we have. Sometimes the ground plane is located outside of the board, so we don't need to place it on the board, and actually we would rather have it outside of the board, using the earth ground as a ground plane, as the reference for the RF signal. In the case of digital signals and also analog signals, we need to provide the reference for the signals so that we can channel them within these channels that we are creating to contain the signal energy and also the signal itself. So signal on the top means return and reference layer on the second layer. Now, if on the bottom layer we have also there a signal layer, so this means that the next adjacent layer is another return and reference plane. So this one should be connected as well to the reference of the signal. So the reference of the signal in this case, I guess, is the ground. So this is GND. So this is the reference for the digital signals. So what does it mean? It means that we have, as a stack up, in here we have signal on the top, GND on the second layer, then GND on the third layer, and then signal on the fourth layer. So this is one of the stack up that I recommend the most, because what we can do also in this case is now we can stitch the first ground and the second ground. So stitching the second layer with the third layer with the ground vias. Like in here, it has been done, maybe not as much as I would like to see, but we see that we have already the stitching here connecting the second and the third layer together. So what this one allows us to do is to have the two layers, so the second and third layer, equipotential with each other. This means that also common mode noise is less likely to appear in between these two layers, because otherwise what we have in here is a difference between the ground on the second layer and the ground on the third layer. And since the cable are connected to this plane, some common mode voltage can rise between these two layers as the signal propagates through the layers. And so this will create some common mode voltage, which creates common mode current, which are super effective at creating radiated emissions. You can think in terms of microamps of current that create some emission which will not allow you to pass the EMC test, because you will go above the limits when you have this type of emissions. So this is super important. So good job, Gabriele, on designing this board with the two G and D layers, because what is common is also with this type of 4-layer stack up is that some designers choose to have the power layer in there. Unless you have high current requirements or low target impedance requirements, you don't want to have the power layer in there, because the current loop needs to be completed. You cannot complete the current loop of the signal on the bottom if you have the power layer in there, because the current will have to complete the current loop through the reference of the signal. It has to go back to the reference of the signal, which in most of the cases, especially in this board, is a GND. So the signal current cannot flow through the power plane through the GND layer without going through the stack up, without going through the impedance that we have between the ground plane and the power plane, because they are DC disconnected. So it will have to flow in the form of displacement current. This will mean that we will have a voltage drop between the power layer and the ground plane. And so this voltage drop, it will propagate in the dielectric between the two layers. This can spread out of the board, and this can be radiated emissions or conducted emissions, which are essentially the same but in different frequency ranges. Okay, so signal layer has a good return and reference plane. These two planes are stitched together. This one can be a little bit improved because we can add more stitching vias in here, so to provide better equipotentiality in between the two layers. But this is already a good job. I already like this stack up a lot. Then what we can improve in here is also creating around these edges of the board, we can create a sort of a Faraday cage with the stitching vias. So we can stitch the vias in here all around the edges of the board and create this Faraday cage effect, which will help us contain the fields inside the board if we place the stitching vias around these copper planes. Then other important point, and I see that I already designed with this a bit more in mind, is that he is providing also the return and reference vias when the signal cross layers, so when they are propagating from one layer to the other. So when the signal propagates vertically, he also has the return and reference, because what happens usually is that we don't have in here the return and reference during the vertical propagation, and then the signal propagate in between the layers, so it's propagating within the two layers in here, and this can create some emissions depending on the signals that we have in here. And don't get fooled by the ADC in here or by the analog signal. Signal propagation acts in the same way, although we want to differentiate the return path for the signals. Then we have some good differential pair designs. These one, they look pretty clean and also coupled together in a way that we want, so that their impedance is constant during the whole propagation of the signal. There would be some variation in here, of course, so this one maybe can be improved a little bit more. Also, I see that we have a different width of the signal trace, and here we have a different width of the signal trace. So we want to make sure that here we have the same impedance for the whole propagation of the signal. So when the signal starts from here, it propagates through the transmission line with the same characteristic impedance. So with the same instantaneous impedance for each point of the transmission line, so that we can have a characteristic impedance. Because at each point of the transmission line, if we don't have the same instantaneous impedance, then we don't have a characteristic impedance, because we essentially don't have an impedance which characterizes the transmission line. So overall it looks pretty clean. Here maybe we can improve a little bit more by feeding this antenna in here. So the antenna is fed in here. This is the antenna part. We want to maybe simulate a little bit in here what happens with the fields, because I see this ground plane is quite close, so this one might interfere a little bit with the propagation of the signal outside of the board, because this is an antenna, so we want to radiate efficiently, as efficiently as possible. So we want to be aware of this ground plane affecting the propagation of the signal outside of the board. Now, what I wanted to take a look is how clean is the layout in terms of crosstalk, because how you can determine crosstalk in here is essentially taking a look at the distance between the signals. So this one you can calculate either with a full 3D simulator, like you can use also some free tool calculator like a Saturn PCB to calculate the portion of this transmission line and see how much cross coupling we will have in here, so how much crosstalk we will have between these lines. I see this is already good because we have already more than 3 times the width of the signal trace, so this is good. Also we have some tuner reference plane in here adjacent to the signal trace, which will reduce the crosstalk for sure. And then we have also in here a close distance between the traces, so between the signal and the tuner reference plane. So what this will do is will reduce the crosstalk between these layers in there, because the fringe fields of the signal will want to stay within the signal traces, so they want to stay under the signal trace as much as possible without propagating to the other board. But to be sure, we need to simulate this board and make sure, for example, in here I suspect there will be some crosstalk already, or here maybe we'll have some crosstalk because they are a little bit too close the signal. So this one can be improved by increasing the distance of the signals traces in here. And we can do the same in the other places, like in here for instance, or in here we can have a little bit more distance between these signal traces, just not to have a crosstalk between these signals, because this can be pretty important. So imagine if you have one of these signals in here which is a reset line. If one of these traces in here triggers, then this one will also see the signal level and it can trigger a reset, or it can trigger some important commands, and this can be extremely important for us because maybe it can reset the board. So depending on the application, this can be pretty dangerous as well. So we want to be careful that we don't have this type of crosstalk within the signal traces. But so far it looks pretty good, and in terms of EMI, it's already having a solid chance of passing EMI at the first test. Also, the disposition of the connector is pretty good because we have all the connectors in here and in here, so that we have all the cables on the sides, and this is already improving EMI because we are not creating dipole antennas by placing, for example, the cables in here and then the other cables in there. Now let's take a look at the 3D view. So you can see we have all the connectors in here and also some connectors in there. This is probably sensors. What I didn't notice in here is that we have also the USB. So USB is located in here. So we also have some connectors in there. Like I was saying, ideally we want to have all the connectors on one side, but some designs they don't allow us to have this type of strategy in here for EMC. So we want to be careful that we then separate the designs properly. So here, for instance, we have all the GPIOs with the ground. I see that you already selected the ground to provide the return for each signals in here, which is good, because like this GPIO 13, for instance, has the return next to it. GPIO 4 also has the return and reference right adjacent to it. And this is super important because if you think about it, for the same reason that we said that we want to have the signal layer adjacent to the return and reference plane, which is this green layer here, the same thing we have to continue outside of the board. So when the signal goes out of the board, we want to have its reference as close as possible, because what happens otherwise is that here, if the signal is going out, the other signal, we need to have have the reference so that we can contain the fields in between these two wires. So we want to have the fields contained in between these two wires in here, because otherwise if I don't place this ground in there, the signal will be here and then the fields will be spreading all over these wires to find the return and reference path. So you want to continue the return and reference path also outside the board so that we can channel the signals in between these two. And so one of the ways to contain it even better is to have this channeling of the fields between the signal and the return reference path is to twist this cable. So when we are creating these twisted cables in here, the fields will be contained in between these two wires. And since they are tied together, we have a better containment of the fields. So that's why this is usually used in analog signals when we have some audio signals, because it also allows us to reject the noise better, because the signal can couple to both twisted wires and we reject the noise that comes from outside interferences, but also from inside interferences. Okay, so I think that for this layout, he uses some solid strategies in here. So maybe one of the things that we can do is to do a quick simulation of this. So we go to fabrication outputs. We want to have the ODB++ files. Compression format is zip. We select a folder and then we extrapolate this board in here, because what we can do then is simulate it by using Symbior software, which will allow us to check for the return and reference for the whole propagation of the signal, so not just on the vias, but also for the entire transmission line. Then it allows us to check also the crosstalk levels. So if we are going to have some crosstalk between the signal traces, then we will have another step, which will allow us to better define the signal integrity performance, which is strictly tied to the EMC performance, because most of the EMC problems are signal integrity problems. So most of the EMC issues that you are going to find in the lab come from the way that you design the board, because if you don't manage and channel the energy properly within the printed circuit board, and then you continue this channeling and propagation of the signals also when you use the wires, so that you are careful about how you channel the fields in between the wires, so not inside the wires themselves, because we are not channeling electrons, we are channeling fields in between the wires. If you are able to channel this field properly, then this will allow you to pass EMC test. So if you design the board that radiates electromagnetic fields, then you can have also issues when outside interferences couple to your board because of the reciprocity between the two modes. So let's try to see what we can do with Symbior. So I open Symbior here, I create a quick solution, so new solution, I just go on next. Gabriela board, then we proceed with importing the project. So here I just select the ODB++ files and then finish the project. So here I can select the board. I think I save it in here. KiCad file projects. And we have in here the ODB++. So let's see. I imported the board as a PCB, click on OK, and the board is imported here. So like I was mentioning before, in here we have several ways to check the integrity of our design. So the first step is to perform the reference integrity violation. So this one will check that the signal has a continuous reference throughout the whole propagation. So it checks the reference potential and that the channel of the signal is continuous throughout the whole propagation. Then we evaluate the impedance continuity. So if the impedance is constant throughout the whole propagation of the signal, because otherwise we will have reflections and other issues related to the impedance discontinuity. And then we have the crosstalk noise. So we can evaluate also how much noise there will be in between the traces. So for instance, how much the noise of this trace is going to couple to this trace in here. So this is the 3-level analysis that we can perform immediately with the Symbior. And then we can have ERC level, fast level, and then also the 3D simulation in here. So we can check signal and the target impedance for the signal traces. Then this one in here, differential links, VS, 2 stitching VS for each differential pair. And then we can evaluate the crosstalk. We can have maybe 100 millivolts instead of 40 millivolts. Then in here we set the condition of the signals. So this is the test signal that we want to use. So here is a 10 gigabit signal. So let's try for 1, and then let's double this one here. So you can see here 9 quick increase the frequency, we can see the frequency sweep will be from 0.01 gigahertz to 6 gigahertz. And you can play around a little bit with these values in here for the signals that you have on the board. So now in here, this is just a quick simulation to show you a little bit of the process and nothing else. So let's select all the signals and then I quickly click on run. So you see Symbio is already performing the whole simulations in here. So you see it's already running simulation for 1415 cross seconds. So let's see how fast this is. You can see it already finished the simulation. So I would say already pretty good results in here. So we have some impedance discontinuities in here. For the rest, look how much it has an impact to have two return and reference plane adjacent to the signal layers. So the stack up in here is already a good stack up. And of course you can go also more in details in here and find the stack up, so you can choose also the materials that you're using. You can refine more the signals in here. But for our purpose today, just to show you a little bit how this works and how you can use these tools to quickly evaluate the performance of your board, this is enough for us. Then let's open the report. What is great about Symbio is that it provides you the report, but it also tells you severity of the problems for the signals that you simulated, of course. Also, it tells you how to fix them. So how you can fix the error that you have. In here, like I was saying, it would be better to have some more stitching vias close to the signals, because you can see number of stitching vias in here. Lacking these reference for the signals are just few, but they are critical, like you can see here. Those are GPIO signals. You can see this is ESP32 MCU. It tells you the location where the problem is occurring with the exact coordinates on the board, and then reference discontinuity. So here it tells us you have a reference discontinuity because you have a cutout in here of the board. So here we have a cutout under, and we need to fix it by routing over a solid ground plane. Then we have in here as well. You need to understand also if this is good results from the simulation, you need to expect already the results of the simulation in here. So you need to know what to expect. Let's put it this way, because here, for instance, this we have the isolation barrier between the two. So perhaps in here, the plane is a little bit too low in respect to where the pad is. And so we have in here some reference discontinuity, but we need to evaluate the case by case in this situation. Maybe in here, this is exactly what we want. So we want to have this separation. Then impedance discontinuities. These are power traces. So this should be a power trace. And then the problem here that this is not categorized as a power trace in the ODB++ files. And this is also why it's important that you define this in the schematic, because like this, when you export for simulations, you have the traces already defined. And so this is not going to be a problem, because you see in here, this is not an issue for us because we don't care much about the impedance of this trace. You see, it's already pretty low, which is exactly what we want. But the software doesn't know this because we didn't tell it at the schematic level. So the schematic should be the primary design tool that we have so that it can guide us throughout to the next steps. And then via hole impedance, in here we have some target impedance is 50 ohm, and here it's a little bit low. So if this is important for us, we want to back drill or optimize this via in here. But look at the crosstalk. The crosstalk for the requirements that we had, which were 100 millivolts, we have zero issues in here. So this means that when the signal propagates, we are not going to see any issues. And this, I would say, is mostly because we have this return and reference plane on the second layer or also on the third layer. So you see the signals are contained between the first and the second pair and between the fourth and the third layer. This is enough. I think that these errors in here can be evaluated one by one and see which one are really critical and which one are not. But also here for the simulation, I selected all the nets. So when you want to perform this type of simulations, you also want to select the appropriate nets. Here I selected everything just to show you a little bit also some errors so that you can see how the tool will show you the errors that we have. So I hope that you find this helpful. And if you want to have more details about the courses that we have, you can head over to fresuelectronics.com and you will find also how to access the academy that we have. So this is the EMI Control Academy, and you will get access to the community where you can ask your questions. You can ask for this type of project reviews. You can also get access to the courses, downloadable resources, the EMC, EMI design course, the tools that you need to understand better EMC and EMI design. So power delivery networks, electromagnetic waves, how they propagate, and signal integrity. Then you have power integrity, emission control with radiated emissions, conducted emissions, EMC pre-compliance, software, everything. It's well explained in here and in engineering terms. If you find find this helpful, just let me know in the comments, and I see you in the next one.